Hello everyone, I am making random recordings now apparently. I'm not going to be in class Tuesday, Wednesday, Thursday, so I'm making videos, kind of a found footage type style, so it might be a little shaky. And you should watch them, because there will be more. I'll be back on Friday. In any case, let's get started.
Alright, so the way this is going to work is I'm going to go through parts of the PowerPoint that I think are the most important for given days. This is obviously the beginning of the PowerPoint. I will be jumping around, but I'll tell you which slides I will be going to if I skip any. We will be coming back to pretty much all of them, but I don't know, whatever. Let's just see how this works. Let's go ahead and go through this.
Alright, just as examples, we've got acids in Coke, stomach acid, vinegar, citrus fruits, and we've got bases in soap, Drano, antacid tablets, Windex, detergent, stuff to clean stuff is usually bases.
So now that you've seen some examples of acids, these are properties of acids. They taste sour like a lemon, they react with bases, you'll see how that works later, and to a litmus paper test, they turn blue litmus paper red. Now, if you see a question that asks what color do acids turn litmus paper, the answer is red. And they are also electrolytic, meaning they conduct electricity. Properties of bases are that they taste bitter, they feel slippery, they react with acids, and they turn litmus paper blue. They're also electrolytic. For some nomenclature of acids, this is all review. You've seen this before, but you may not remember it, so let's just go through it again real quick. Acids are composed of a hydrogen ion, the H+, followed by an anion. So if you have hydrogen plus and Cl minus, you get HCl, or hydrochloric acid. H plus SO4 2 minus is sulfuric acid, H2SO4. Binary acids are just two elements combined together to make an acid. H plus an anion with an "ide" ending means that the acid name is hydroblankic acid. What goes in the blank is the root word for whatever acid you have. So HCl, the anion is chloride. So you take chloride, take off the "ide", replace it with "ic", and you get hydrochloric acid. So again, you've hopefully seen this before, but maybe you don't remember, so have a review. As another example, HF, you've got hydrogen and fluorine. Your anion is fluoride. So if you take fluoride, bump the "ide" off, turn it to "ic", you get hydrofluoric acid. Oxyacids are a little bit different. They include more elements than just two. So H plus an anion with 8 at the end of it, you get an acid name of blankic acid. So it's just like the binary acids, but without a hydro at the beginning. So HNO3, your anion is nitrate. You can look on the back of your periodic tables for that. And therefore the acid name is where you take the nitrate, take the 8 off, replace it with ic, and you get nitric acid. Again, you should know how to do this, but this is all review. Another example, H2SO4, anion is sulfate. Take sulfate, take the 8 off, put on ic, you get sulfuric acid. Ite sometimes is at the end of oxyacids, and ite turns into us. Hopefully you remember that too. So for example, HNO2, NO2 is nitrite, ite turns into us, and you get nitrous acid. There's some extra practice on this PowerPoint. Just do whatever you want. It's all here. You can take the different anions, turn them into the acid, but notice what you put on the anion to make it an acid is hydrogen. It's always H+. As for the nomenclature of bases, we've done a little bit of this, but not all that much. Bases are composed of a cation followed by hydroxide. Now and then you'll get a base without hydroxide, but chemistry is the science of exceptions, so let's just say usually it has that OH-. So writing base names, the rule is name the cation and add on hydroxide. So NaOH, sodium hydroxide. Right? MgOH2, magnesium hydroxide. FeOH3, iron 3 hydroxide. In this case, iron is a transition metal, so you have to add in that little Roman numeral thingy. The one major base that we're going to look at that does not have OH in it is ammonia. If you see NH3, know that this is a base. Yes, it has H in it, and normally acids have H in it, but NH3 functions as a base. So remember that, that's ammonia. Writing some base formulas, you got potassium hydroxide. You can do this on your own if you want, so I'll wait here for a second. Okay, you should be done because you can have a pause feature on your video. K, formula, KOH, because put the K with the OH, and there you go. Calcium hydroxide, Ca+2. Remember that OH goes in parentheses, so that means there's a 2 on the outside, crisscross method. Hopefully you remember that. Aluminum hydroxide, aluminum has a +3 charge. Do the crisscross method, you get AlOH3. All right, now I'm going to go through a few slides that may not really look like they have anything to do with your homework, but I'm going to cover them now anyway. When ions are in solution, you can ask the question, why are some solutions acidic, basic, or neutral? So we were talking about ions with K, OH, and other things like that. So what determines whether it's acidic, basic, or neutral? It all depends on how much H+ and how much OH- are present in the solution. So H makes an acid, and OH makes a base. In an acidic solution, there are more H+ ions than OH- ions. There's some examples down there. In basic solutions, they contain more OH ions than H+ ions, so it's the other way around, and there's more examples. In a neutral solution, there are equal amounts of H+ and OH-. The key with this is that the most common neutral solution that you know of is water, H2O. H plus OH makes H2O because you have two H's and one O. Therefore, once you put an acid and a base in equal amounts together, you get water, which is completely neutral. That being said, you can take water and have it self-ionize. So if you take H2O, you can split it apart between H+ and OH-. This is a simplified version of how this works, but it gets the point across. The next slide in this presentation is types of acids and bases. You've got Arrhenius, Bronsted, Lowry, and Lewis. For the sake of this portion of the PowerPoint, skip this, go to slide 25 right there, where it says Bronsted-Lowry model. We're going to skip Arrhenius for the moment. We're not going to do Lewis either, but this we're going to do right now, and we'll come back to the other ones later. So the Bronsted-Lowry model, or if you want to use the umlaut that is not above this O, Brunstedt-Lowry, because I think he was German, you can have a Bronsted-Lowry acid where a proton, or an H+, is a donor, so it can give H+ to another species, or a Bronsted-Lowry base, which is where you can have a proton acceptor. Now, H+ and proton are basically the same thing. If you look at your periodic table and find hydrogen, just H+, you can see that that only has a proton in it. There's nothing else to it. There's no neutron, there's no electron, therefore H+ is a proton. So here is something to remember. Absolutely remember this. Acids donate protons, bases accept protons. Do not forget this. This is very important. If you want an acronym, or whatever you want to call this, something that lets you remember, Abigail doesn't buy apples. Sure, if that helps you remember, do that. Come up with another one if you feel like it. So some examples. HCl plus H2O goes to Cl- plus H3O+. What's happening here is that the H2O accepts the proton from the HCl. That brings up the question, which is the acid, which is the base? And the acid is what donates the proton, so the HCl, that's the acid donator, and the H2O is what accepts the proton. So if you look over here, the H3O plus has accepted the hydrogen from the HCl, and therefore the H2O was the thing that accepted it. If it accepts it, it is a base. That was the whole Abigail doesn't buy apples thing. Acids donate, bases accept protons. Here's another example where you have NH3, a base, and H2O, which is neutral. So if NH3 accepts a proton off of the hydrogen, what you can have there is a base, which is the NH3 because it takes the hydrogen, or it takes the proton, and the H2O gave it up, therefore it donated that proton. The next slide is the Lewis model. Let's skip that, at least for the moment. We'll come back to it later. But for now, jump to slide 31. Slide 31 is conjugate acid / base pairs, and this is something having to do with your homework for tonight. A conjugate acid is a new species produced when a base gains an H+ ion. A conjugate base is a new species produced when an acid donates an H+ ion. So if you remember a few slides back when we tried to figure out which one was an acid and which one was a base according to where the proton moved, now we can see what the name, so the conjugate acid or conjugate base of the product is. So in a general Bronsted-Lowry reaction, we can just say this is what it'll look like in general. The acid will turn into the conjugate base. The base will turn into the conjugate acid. Just to pause real quick, conjugate means paired or combined. So if you see here, a base forms a conjugate acid because the base and the conjugate acid will always be paired. They're always going to be together. Same thing with the acid and the conjugate base. Acid and conjugate base go together because that's how it works. Conjugate means paired or combined. So every acid has a conjugate base, every base has a conjugate acid. That's the moral of the story. As an example, you've got nitric acid plus water goes to H3O plus NO3 minus. Figuring out which is the acid or the base has to do with the composition of whatever you have over here. So notice you've got an H at the beginning, making this an acid. If the HNO3 is the acid, the other thing that's right next to it is the base. The base accepts the proton from the HNO3 and you get H3O plus over here and NO3 minus over here because of the transfer of the proton. And what you get in terms of conjugates is the H3O plus is the conjugate acid because it was the base, and the NO3 minus is the conjugate base because it was the acid. That's how it works. There's a little pictorial representation if you want to see how that works or looks. As another example, NH3, this is the thing that you have to memorize. NH3 is the base, and the H2O is the acid. A base accepts a proton, so since the H2O is an acid, it donates that proton to the NH3, and you get NH4 plus OH minus, resulting in NH4 plus being the conjugate acid and OH minus being the conjugate base. And there are the arrows for you. You can do this a slightly simpler way. You can just take a look at H2SO4 and say the conjugate base of that. That's HSO4 1 minus, or minus. The way you get a conjugate base, the simple way of describing it is lose a proton. To form a conjugate base, just lose a proton. So H3O plus, lose a proton, H2O. There you go. So another one. What is the conjugate acid of HPO4 2 minus? Pause the video, try to figure it out. Okay, you're done pausing. It is H2PO4 1 minus. This says conjugate acid. That means instead of losing a hydrogen, it had to gain one. That's why we have H2 here. OH minus gained a proton, so we should have H2O, and there you go. So that raises the question, how can H2O be both an acid and a base? This is what we call amphoteric, something that can act as both acids and bases. H2O acts as a base right here because it's coupled with an acid over there, and H2O acts as an acid in this case because it's paired with a base. H2O has a pH of 7, meaning it's completely neutral, therefore it can function either way. The next slide is mono, di, and triprotic acids. Definitions are on here, but let's skip these for the moment because that's pretty much all you need to know for tonight's homework. I will have another video out tomorrow explaining some extra situations, just if you like the lovely sound of my voice. And you'll see how this works. I will see how this works. Hopefully this works. So now my suggestion is to work on your homework, post any questions you have to Edmodo, and